Alright, welcome everyone to the next lesson in this series, and in this video we will look at advertising IP pools to an underlay network using Calico and BGP. Now before we proceed with the lab, let's look at why you may want to consider this. Now, in a situation where you have the nodes in a Kubernetes cluster spread across multiple network segments or multiple VLANs, we looked at how you need to have an overlay network for pod-to-pod routing in a previous lesson. Now, if you advertise your IP pools to the underlay network, you need not have that overlay network, and thereby you can get rid of the overheads associated with the overlay. So that tends to be a common use case for this. Another use case is if you have external workloads in your network that need to have direct reachability to pods in the cluster, you could advertise the IP pools associated with those pods to the underlay network. So consider a scenario where you have a workload, a pod, for example, in the cluster that has a static IP address, and you have other workloads in your network that needs to connect to that pod or workload using the static IP. This tends to be a common use case, especially when you deploy VMs using KubeVirt in a Kubernetes cluster, right? So with those examples in mind, let's move ahead with the lab and look at how you could do so with Calico and BGP. Let's get started. Okay, so this lab can be found in the 10-Calico-BGP-IP pool folder. So if you clone the repo, if you navigate to this folder, there is a deploy script. Now in my environment, I've already gone and executed the script, so my lab is provisioned. Now, once the lab is provisioned, you could run this command just to make sure that the container lab topology is up and running. I know the output on my right is a bit unruly. I have a similar output here on the left as well. So this is the topology. We have a 4-node cluster in this case with a top of rack, a switch. The topology is represented or depicted in this image here as well. So 4 nodes, 2 VLANs, and we have the control, worker 1 and 2 connected to VLAN 10, and worker 3 connected to VLAN 20. And these VLANs, they have their default gateways in this router. And we will next peer these nodes with their respective default gateway IP addresses. Okay. All right. So once you've inspected the topology, make sure you export the kubeconfig file as well so that you can access the cluster API. And once done, you could issue commands like kubectl get nodes. And in this case, you see that we have our 4-node kind Kubernetes cluster up and running. Okay. Now the script has gone ahead and provision all the manifests as well. So we have a fully functional topology. So let's inspect the configurations for this lab cluster here. First of all, let's look at the installation resource and the IP pool configured in that resource. So if I do a kubectl get installation -o YAML, I'm just going to go to the top here. If you recall, we provide the installation resource as an input to the Calico install, and we also specify the default IP pool. And in this configuration that we've passed, if you look at the default IP pool, there are a few important things to note. The first one is NAT outgoing is disabled. Now, typically when a pod in a cluster, when it sends out egress traffic, we enable NAT outgoing so that it gets natted to the IP address of the node, because your underlay network isn't aware of these pod IP addresses. It wouldn't know how to send the return traffic. Now, given that we are making these IPs routable in the underlay network, we need not NAT outgoing traffic. So we've disabled NAT in the default IP pool, right? So that's the first thing to note. The second one is we've configured disable BGP export to false. And what this means is we will use BGP to export or advertise the IP blocks in this IP pool to the underlay network. Okay. Now, encapsulation is also set to none, which means Calico will not deploy an overlay network for pod-to-pod routing. And that's because these IPs would now be routable in the underlay network. Okay. So a few important parameters to note. Now, if you want to look at the exact file that was passed to the installation, you could navigate to this folder here where we have all the CNI config resources. And if you look at the custom resource.yaml file, this is the installation resource that we pass to the deploy script to provision Calico in this particular cluster. Okay. All right. So with that, let's look at the IP pools in this cluster. So we have the default IP pool, and the default IP pool is provisioned by the Calico operator. It takes in the installation resources as an input, and based on the specifications of that resource, it configures the default IP pool. And we have a load balance IP pool here as well. You can ignore this for this lab. We used it in a previous lab. And so once the IP pool is configured, you're probably already aware that Calico then configures block affinity. So it breaks that IP pool into smaller blocks and assigns those blocks to the nodes in a cluster. We looked at that in the IPAM lesson. And these are the block affinities assigned to the nodes in this particular lab environment. The reason this is important to note is because when you look at the individual nodes in the cluster, they're going to advertise the prefixes for the block affinities that have been assigned to them by Calico, and we will look at that shortly. Okay. All right. So with that, let's look at the BGP configuration for this particular cluster. Now, the AS number is 65010, right? And it's the same AS number we used in the BGP lesson as well. So if you've not looked at the BGP video, please go ahead and have a look at that. The configuration is more or less the same. And the only difference is that in this BGP configuration resource, we've also specified a prefix advertisement. And we are basically instructing Calico to advertise the cluster side, basically the side of the default IP pool, which is 192.168.0.0/17. So if you look at the default IP pool, the one that we passed in the installation resource, our CIDR was 192.168.0.0/17. So we're basically instructing Calico to advertise those prefixes with this community. And in BGP, communities are a way of tagging the prefixes that you advertise. You can then match prefixes based on these communities and do various treatments to those prefixes in your upstream router. So we're providing this a community value here as well. Okay. And we're also advertising the service load balancer IP range, which we looked at in a previous lesson. The important thing to note is this particular configuration over here. All right. So with that BGP configuration for this cluster, let's next look at the BGP peers, right? So in my case, I have two BGP peers, one for VLAN 10 and one for VLAN 20. And if you look at the BGP peer configuration for VLAN 10, we have a node selector which says VLAN equals 10. And that's because if you look at, let me say dash or wide here, if you look at the nodes in this particular cluster, and let me say -- show labels, I know the output is a bit unruly here. Let me see if I can improve that a bit. So if you look at the labels in the nodes in this cluster, you're going to note that depending on which VLAN the node is configured to, there is a label associated with that node. That way we can easily identify the nodes that are in a corresponding VLAN and then use those labels for BGP peering as well. Okay. So if you look at the BGP peer for VLAN 10, we are peering nodes in VLAN 10 based on their labels to 10.10.10.1, which is configured as the BGP peer IP, right? Similarly, if I look at the second BGP peer, which is on VLAN 20, again, based on the node label, we are peering it to 10.10.21. And the reason we have like different peers depending on the VLAN to which the node belongs is in actual environments, you would have top of rack switches for different nodes in the cluster, and you would want those respective nodes to peer with their respective top of rack switches, right? So you need a mechanism whereby you could scope the nodes and define a peer for those nodes. So you need to make sure that you have some kind of labeling scheme for your nodes that make it easy for you to scope your nodes. And in this case, I have done so in my kind cluster by providing each of these nodes a label specific to the VLAN they belong to. Okay. And if you want to look at that in the kind cluster configuration, you can go to the kind setup, which is this one over here. So let me just cut that. And in my kind worker node definitions, I've provided a node label. Okay. All right. So with the BGP PS configure, I now have my respective nodes, peering with the top of rack switch or router here. And what I can do next is I'm going to exec into that router, which is our Arista CEOS image. And I'm going to look at the BGP configuration in the router. So in the router, I am configuring a couple of listen ranges. So the thing with a listen range is I need not specify individual node IPs. Instead, I give the router a listen range, and any BGP peering sessions that it receives from these ranges will be accepted. And I have also configured certain other parameters for these listen ranges. Most importantly, this router will act as a route reflector for the nodes in this cluster. So what do I mean by that? So a route reflector basically propagates the prefixes that it receives from one neighbor to all the other neighbors configured as route reflector clients. So for example, if the control node here advertises a prefix, the route reflector will make sure that prefix gets advertised to other nodes in return. Typically in an IBGP session, that doesn't happen unless you have a particular node or a particular router configured as a route reflector. The objective for us here is to make sure that each of the nodes have routes to the corresponding remote nodes for their respective IP blocks. Okay. And I have also configured the next hop as self. And what that means is as this route reflector advertises the prefixes back to the other nodes in the cluster, it's going to inform these nodes to send the traffic to itself if these nodes want to reach out to pods that belong to the IP block that is in the control node as an example, right? Now, there are other variations to this as well, but in this case, I have configured this as next hop self. Just bear in mind that depending on your topology, there are many things in this setup that you can tune, but I'm just going to keep it simple for this lab. Okay. All right. So with that configuration, and as part of this BGP setup, I'm also advertising the respective networks in VLAN 10 and 20 to these nodes as well. So for example, if control node 1 wants to connect to this node in VLAN 20, it has a route for that as well, learned by the top of rack switch in this case. Okay. So yeah, so just I mean, the BGP configuration for top of rack will depend on the type of router that you're using. In this case, we are using an Arista CEOS image. Okay. So with that configuration in place, what we can do is we can do a show IP BGP summary and look at the neighborships that are currently established with this router. And you can see 4 neighbors, and these 4 neighbors correspond with the 4 nodes in this particular cluster. And you can also see the messages sent and received, as well as somewhere here there should also be an output for the number of prefixes that this router has learned from each of these nodes over here. Okay, and it's learned 2 prefixes. In this case, the 2 prefixes correspond with the IPAM block as well as the load balancer IPs it has learned from these nodes. So this is what the setup looks like. So we have the top of rack, the router in this case, the CEOS image. I'm sorry, I know I'm referring to this using multiple names there. And we have each worker with an IBGP peer. This is a route reflector. So if a worker or a control node in this case advertises a prefix, this router will make sure that prefix is propagated to all the other nodes as well. And also while doing so, it'll instruct these nodes that the next hop in the event these nodes have to forward traffic to that prefix would be the router itself. So the traffic gets forwarded to this router. And these nodes advertise their respective, IPAM blocks to this upstream routers. If I do an IP route, you will see the respective IPAM blocks that have been advertised by the respective nodes in this lab. And this is what this setup looks like. So each node in the cluster gets allocated a IP block affinity by Calico, and each node will then advertise a prefix for that corresponding to that IP block to the top of rack. And the top of rack in turn advertises those prefixes to all the other nodes in the cluster. So if we look at the top of rack, we see the advertised prefixes. And if we exit from this router, and apply this manifest, in my case, I've already done so. What this does is it creates a Calico resource that you can then use to validate the routes in a node as well. So what I've just done here is I've executed a command to look at the routes in the control node in this cluster. And if you look at the route, we have 3 routes corresponding to the 3 block affinities assigned to the rest of the nodes in the cluster. And you see that this node is now aware of those routes, and the gateway for those routes are configured as the top of rack switch. So ultimately what this means is, as an example, let's say a pod in the control node wants to connect to a pod in worker node 3 as an example. It's going to send that traffic to the router, and in the router's routing table, it will have an entry pointing to worker node 3 for that respective prefix, right? So that's how end-to-end routing is achieved, okay? And you could verify this for each of the nodes, and you're going to see like 3 route entries corresponding with the IPAM blocks of the rest of the 3 nodes, in the cluster, okay? All right, so with that, what we're going to do next is I'm going to exec into the control node, and you can look at the routing table in the node as well. So if I do an IP route grep bird, you're going to see, just ignore the black hole route. The black hole route is basically a route that gets configured for the block affinity assigned to this particular node. And the reason we have a black hole is because if you remember, if you look at the routing table for pod IPs in the node, you're going to see a specific route to a Kali interface, right? And everything else will get black holed. And if you look at the rest of the routes learned by Bird, which is the BGP daemon in this case, these routes correspond with the IPAM blocks of the rest of the nodes in the cluster, and they will be routed via the gateway, which is 10.10.10.1 in this case, which is the gateway for VLAN 10. Okay. Alrighty. So with that, what we can do next is we can test some connectivity. What I'm going to do here is I am going to first find out. So in this particular cluster, so before that, if I do a kubectl get pods, I have these multi-tool 1 pods. These are running as a daemon set, so they're deployed in all the nodes in the cluster. So what I'm going to do is I'm going to find the IP address of one of these pods scheduled in worker 3, because worker 3 is in a separate VLAN here, right? And the IP of the pod is 192.168.46.129, okay? And I'm going to also find the IP of a pod that is scheduled in worker 1. And that happens to be 192.168.42.193. And now I'm going to exec into, let me just copy this, exec into the multi-tool pod in worker 1, and I'm going to ping the multi-tool pod which is scheduled in worker 3, and you see that the end-to-end connectivity works, which means through this topology we have end-to-end routing. In this case, I tested from worker 1 and worker 3, and you could do similar tests from other nodes as well and confirm, end-to-end routing. So this is how the routing works. Just to reiterate, we were pinging from this pod to this pod over here. And if you look at the life of the packet from multi-tool 1 in worker 1, let me see if I can zoom this diagram a bit more. All right, so for multi-tool 1 from worker 1, the packet goes to the host, which is the worker 1 host, right? So from the pod, the packet goes to the host. The host does a lookup and sees that the next hop is the top of rack switch. So the packet goes to the top of rack switch. the top of rack switch, or the router in this case, the CEO's image, does a lookup and it sees that there is a route for that range pointing to worker 3. So it sends the packet to worker 3, and worker 3 then will have a specific route for that specific IP pointing to the Kali interface of the multi-tool pod deployed in worker 3, right? So that's how the packet gets routed end to end, and the same lookup happens for the return packet as well, okay? Now, one of the important things to observe in this whole process is that when you look at the routing table in the node, you don't see an overlay network, right? So if you remember when we looked at the VXLAN or the overlay lab or lesson, in the route entries in the node, you see that the next hop is the VXLAN interface, right? And that's how the packet gets routed through the overlay. In this case, there is no overlay involved. The packet without any overlay, without any NAT, gets sent to the top of rack switch, and that switch or router then makes a forwarding decision. So basically the IPs of the cluster are first class citizens in your network in this case, okay? Alrighty, what we can also do is just to confirm that the IPs are in fact first class citizens. Let's exit from this node and exec into the router in this case. And from the router, you can directly ping pods as well, right? And typically in a cluster, you wouldn't be able to do this. If you remember, the IPs of a pod are self-contained to the cluster. But in this case, the IPs are now available for other workloads in your network as well, and they can directly connect to the pods if required, okay? All right, so that's it, for this lesson. There's a lot we can talk when it comes to BGP. I just wanted to give an introduction in this particular lesson, and I probably would have certain follow-up lessons as well that dives a bit more deeper into the BGP capabilities of Calico. But that's it for now. I hope you enjoyed this video. Thanks for watching. I'll see you in the next one. Bye for now.